In this second video on the crystal chemistry of ionic structures, we turn to more complex ionic materials and introduce the so-called polyhedral model to show how, compared to traditional ball and stick models, the polyhedral representation is more effective in depicting the more complex structures of ionic materials such as TiO₂, Al₂O₃, and manganese dioxide. We'll see that by using fairly straightforward principles, many materials that may otherwise look quite distinct and different in their structures actually have very closely related crystal structures.
Now we'll consider the polyhedral representation of ionic structures, and our example will be limited to octahedral sites in close-packed anion frameworks. We're familiar with the previous pictures we've shown, where we use spheres to represent the atoms, and as we place the second displaced close-packed layer on top of the first, we can identify the octahedral environment of a cation. So for example, this cation in blue has 3 neighbors below it and 3 above it. This is abstracted from the framework here, highlighting that arrangement. We'll see that it can be simpler than instead of drawing spheres for everything, that we can start to use a polyhedral representation. So for example, rather than focusing on the spheres themselves, we're now going to focus on the polyhedral environment. And so for just one layer, here what I've shown is a series of triangles surrounding each sphere. They're meant to represent the bottom of the octahedron, such that for this cation, its neighbors are this triangle here. Now I'm showing the environment of that cation. The 3 anions below it, now shown in red, are here. Here's my triangle. And when I add the next layer on top, I'll see that that triangle, if you like, is inverted. And these are the anions that are nearest neighbors to the cation in the layer above. So in the polyhedral representation, which is widely used for inorganic ionic materials, we use cation-centered polyhedra to represent the structure. And in fact, the size of the anions in these pictures is artificially reduced. Indeed, in some cases, they're not even shown, to focus not so much on the spheres, but the polyhedral connectivity. So here I'm showing a unit of 2 polyhedra, octahedra. Here's my cation in the middle, showing its bonds to its 6 anion neighbors, which are at the vertices of an octahedron. I've shrunk the size of these anions, as I just mentioned, way down. And now I can see that in this case, I'd have a cation octahedron sharing an edge with another octahedron, because these 2 oxygen anions at the edge here of this octahedron are also at the edge of this one. Let's first look at the Rocksalt structure, but in this case, we'll focus on a polyhedral representation. We know all the octahedral sites are occupied by cations. And now let's just look at the sharing. So back to the sphere model. Here's my cation. Here's the base of its octahedron. This anion is shared by this octahedron and also the octahedron of this cation. And when I add the next layer on top, in the sphere model, the other shared anion is shown here in the top layer. So these are in orange, these are the 2 anions that are shared by the octahedral environment of this cation and this cation. Well, this type of picture gets messy and confusing. And that's why we turn to the polyhedral representation, to highlight the octahedral sharing, in this case the edge sharing for the Rocksalt structure. And so now, if I represent this sphere picture by polyhedra, this is what I get. I get rows of sodium, if it's sodium chloride, octahedra, sharing edges and then connected to rows behind it, again through edge sharing. So we're showing the same thing in the 2 pictures, but the lower picture is focusing on the cation connectivity and the connectivity of their octahedra in this case. So this would be the polyhedral representation of the complete 3D Rocksalt structure. In this is just a view of the face-centered cubic unit cell, where all of the edges of every octahedron are shared by neighboring octahedra. In red I outline one face of the unit cell. So I have sodiums on the corners and another sodium in the middle, the typical face-centered arrangement with the anions in between. So I can see that this picture is the same as the previous ball and stick model, if you like, of the sodium chloride structure, but here the view shows us a little bit more about the connectivity of the octahedra. There are different types of polyhedral connectivities that we'll see in inorganic structures. We could have isolated octahedra in some cases in which there is no sharing. In this case I have corner sharing, where this anion is shared by both octahedra and it lies at the corner of each. This is the edge sharing that we just showed, where this edge is shared by the two cation polyhedra. And then I can also run into face-shared octahedra, where the face of one is common to the face of another. All three examples are found. One thing as we progress from corner to edge to face sharing, we'll see that we're decreasing the cation separation. And the actual cation-cation distance is getting shorter as I go from left to right. That can, in some cases, be a source of destabilization. And often we'll see in face-shared octahedra that these two cations do not necessarily want to be that close, and they'll become off-centered. They'll move off the center of their octahedra. This cation going up, perhaps, and this cation being displaced slightly in a downward direction. That, in turn, can actually yield to some rather interesting functional properties. So for the sodium chloride structure, because all of the sites are filled, the polyhedral view is a little bit cluttered, and it's maybe not too useful. But now we'll see it's very useful for representing and understanding the structures of other systems that have lower site occupancies. So let us turn to some of those now. So we'll begin with AX2 octahedral structures. Again, we're going to keep tetrahedral sites out of this. Here's our familiar picture where all of the octahedral holes are filled with a cation, and we know the stoichiometry of this system would be like sodium chloride is AX. Now for AX2, we're going to remove half of those cations, and we'll do it in a logical way. We'll remove every other one from each line, and that is shown here. So here is my result of removing every other octahedral cation. So because I've done that, the octahedral interstices are only 50% filled by the cations. Here there is an interstice, but it's vacant. There's no cation in it. So in this case, the stoichiometry of this layer would be AX2. Now let's move towards a polyhedral view by first just showing the base of the octahedron and showing the three anion neighbors of each cation. And we see that in the structure we're starting to get these chains of octahedra in these directions. If I repeat this in 3D with an anion stacking that's AB, AB, then this is actually the structure of TiO₂, and it's called the Rutile structure. So now let's use the polyhedral representation to give us a better look at the 3D structure of rutile. We've seen this picture before. Then if I put the next close packed layer on top, going from AB stacking, it would look like this. Now let's look at the polyhedral view of this layer. And it's shown here. Here are my chains of octahedra, each sharing an edge. And each chain is separated by a row of those vacant cation sites. So in this polyhedral representation then I have these edge-shared, if you like, octahedral chains. So now let's build the 3D structure, and we're going to do so with AB-AB type stacking of the close packed layers. Each layer of octahedra is going to look just like this, but when I put the next one on top, it actually locates the chains on top of these vacant sites to minimize the cation repulsions. So let's do that. They go on top. And now if I look at the 3D view looking in a perpendicular direction, this is my resultant structure of rutile. Chains of edge-shared octahedra separated by vacant cation sites, repeating in one layer. The layer below, they are shifted in this case to the right, such that this chain of octahedra are corner shared, to the layer above, but lie below the vacant sites, and then it repeats. So we see for rutile, which is the structure of TiO₂, as I've mentioned, but also many other AX2 chemistries, we get these one-dimensional channels, if you like, or openings in the structure. And there's some interesting things you can do with a structure like this. It's possible to insert lithium cations into these channels, the charge being balanced by some reduction of Ti4+ to Ti3+. And indeed, TiO₂ with the rutile structure has been looked at an electrode for batteries. Let us look at some other filling schemes, structural types that are adopted by other compounds. This is another 50% filling scheme, where again half of the octahedral holes are occupied by cations, but in a different way. Here we'll see that we're getting these zigzag rows of the filled positions, separated by zigzag vacant sites. This is the arrangement in the so-called alpha PbO2 structure. Let's go to our polyhedral view, shown here. So now I get these zigzagging edge-shared octahedra, separated by a zigzag row of vacancies. And when I build up the 3D structure, the next layer on top goes on top of these vacant positions, just like we had before, shown here. And then if we look at the perpendicular view, this is what we have. These are our layers, shown here. This is my second layer, displaced with respect to the first. And the final 3D structure is as shown. In this case, we don't see any well-defined open channels, and indeed this structure is not amenable to insertion of, for example, lithium. Another common structure is corundum. A2X3 is the stoichiometry. It's the structure of Al₂O₃ and also Fe2O3, two very important ceramic materials. Well, in this case, to get the correct stoichiometry, we must only fill 2/3 of the available octahedral positions. So as I go along a given row here, I fill, vacant, fill, vacant, etc. And I do that in each case, but I displace these two with respect to these just to try and again minimize the cation-cation repulsions. So this is the arrangement of the aluminum cations in aluminum oxide. Now let's go to the polyhedral view. There's the base of the octahedra in the sphere model. Here's the polyhedral model. Again, we'll see the correspondence between the two. 2 octahedra here. Here's my 2 complete octahedra sharing an edge. There's nothing at the center of this space. That's where I could have put another cation, but because of the stoichiometry, there's nothing there. And then the 2 repeat. The next layer down, everything's just displaced over, and then it just keeps repeating. So again, this is the arrangement in one layer of Al₂O₃, but it's not a layered structure, it's 3-dimensional. So again, the next layer up is displaced with respect to the first. Here it's not possible to make sure that every cation in the second layer goes over a vacancy in the first, and the resultant 3D structure is the one shown here. As it turns out in alumina, there is some phase sharing of the octahedra, and if we look very closely at this picture, we'll see the signs of that, and a phenomenon I mentioned earlier, that when 2 octahedra share their faces, the cations, to minimize their repulsions, will move off center and just displace a little bit. And hopefully that's evident to you in this picture. This aluminum has moved down a little bit. It's lengthened these 3 oxygen bonds and shortened these. This one has done the opposite, and we've been able to at least maximize the distance, or make the distance, the separation between these 2 alumina cations larger to minimize their repulsions. There are some ordered variants of the corundum structure, and that is a very well-known structure type called ilmenite. So if we take Al₂O₃, and if we replace the 2 aluminum cations by a coupled substitution of one 2+ cation and a different 4+ cation, we'll see that we're still charge balanced. So instead of having 2 identical cations, I have 2 different ones. And when I do this, if the 2 cations, A and B in this case, have different valencies, which here they do, and different sizes, they tend to order into separate layers of the corundum structure. And that ordered structure is called ilmenite. So here's the picture of ilmenite. Let's look at this layer, identical to corundum. So is this. But this is where my A cation is going, and my B cation orders in this layer, and then it repeats with this ordered AB-AB arrangement. And there are many examples of this type of structure. Titanates of iron, magnesium, nickel, and manganese. Another set of interesting structures are those of manganese 4 oxide, MnO₂. MnO₂ is a very important material. It has many applications, such as in dry cell batteries, and it's the basis of many cathodes in rechargeable lithium batteries. Let's take a look at the structures of MnO₂, because there are several different forms, and they've been very well studied. The first is called pyrolusite. It's actually the same structure as rutile. Indeed, MnO₂, TiO₂, the same stoichiometry. So here again is my rutile structure, just showing the arrangement of the octahedra in one layer and the resultant 3D structure. And as I mentioned before, we get these tunnels or channels in the structure. And here they're 1 by 1 tunnels. In other words, the dimensions of the tunnel are 1 octahedron by 1 octahedron. Another form of MnO₂ is ramsdellite. And we'll see this has 2 by 1 tunnels. Let's first look at the arrangement of the octahedra in one layer of ramsdellite. Now, instead of just these single channels isolated by vacancies, we have 2 rows of octahedra connected by edge sharing to each other. That's followed then by 2 rows of vacancies, shown here, and then it repeats. The next layer on top, the chains sit on top of the vacancies, and then we'll twist it and look at the resultant 3D structure, and we see well-defined channels. So this is the layer 1 if you like, layer 2 displaced, so the octahedra sit above the vacancies of the first layer, and the result is a rather beautiful structure with very large open channels. 2 by 1 because the dimensions of the channel is 2 octahedra in this dimension by 1 in this. So there's more space here than there is in pyrolusite, and therefore we might think this would be even more attractive for inserting various species into the structure. Another form of manganese oxide is called todorokite, shown here. In this case, the arrangement is such that we get 3 by 3 tunnels. So in this case, these one-dimensional channels are 3 octahedra by 3 octahedra, and there's a huge open space here. And here we can not only insert lithium, but even larger molecules, because the structure has a very large nanoporosity. And as a result, this structure is rather interesting for its applications as membranes and as battery electrodes. So, one chemical formula, MnO₂, but depending on the arrangements of the polyhedra, many different possible structures with different interesting geometries.
Let's take a look at one last structure, which is the AX2 stoichiometry. We'll assume the A cations are in octahedral sites, and so from the stoichiometry we should now be comfortable deducing that 1/3 of the octahedral sites will be filled. And here's a whole series of fluoride examples of this particular structure. Let's build this up from the fully occupied octahedral sites by occupying every 3rd site. Get rid of 2, 2 more, 2 more. We'll keep on doing that in a systematic way to maximize the separation of the cations, and we'll end up with the AX3 arrangement found in these compounds, and there is the repeat unit. So again, a similar principle that can yield the correct structure. Another interesting thing about this layer arrangement is actually the symmetry of the filling pattern is identical to that we had seen in Al₂O₃, the corundum structure. Though in this case, in AX3, 1/3 of the sites are filled, and they're in the same positions as that 1/3 empty sites in Al₂O₃ shown at the bottom. So this is the structure of corundum, and I'm just highlighting the sites that are empty, and we see this symmetry is identical to the filled sites in the AX3 structure. The layer stacking in the AX2 Octahedral structures follows the similar principles we've seen before in Rutile and other structures. So here's the polyhedral view of one layer, 1/3 of the octahedral positions filled. Then when we put the second layer on top, then the cations in that layer are shifted so they're over the unfilled sites in the original layer, shown here. But now it takes 3 layers to cover them all up, if you like. So here's the third layer, again shifting over so the third layer cations sit above the open sites in the second, etc. Here's then the view of the structure looking at the layers edge on. And we can see in the 3D structure again there's some open channels. And again this particular structure has been examined to see if it has applications as a potential cathode in lithium batteries, with lithium going into those open voids and reducing the ion from iron 3+ to iron 2+ to charge balance.